Imagine a tower so tall that its peak reaches beyond the clouds, connecting Earth to the heavens. This ambitious concept brings us to the intriguing intersection of geostationary orbit, tensile strength limits, and groundbreaking carbon nanotube ribbons. Today, we explore whether this sci-fi vision could indeed surpass rockets in transporting materials to space. To begin, let us understand what a geostationary orbit is. This orbital path lies approximately 35,786 kilometers above the Earth's equator, positioned such that a satellite or object appears to hover at a fixed point in the sky. This specific orbit moves synchronously with the Earth's rotation, making it a prime spot for telecommunication satellites. Picture it as a vantage point in space that remains perpetually above one location, akin to a watchtower observing the same stretch of land. At the core of the space tower concept is the challenge of material strength. Any structure reaching from the Earth to a geostationary orbit requires a material that can withstand immense tensile forces, the kind of forces that stretch an object before breaking it apart. Many materials falter under such demands. Imagine pulling a vine across a cliff, only to see it snap, a vivid demonstration of nature's tensile limits. Enter carbon nanotubes and graphene. These materials represent a leap forward in our quest to conquer tensile strength constraints. Carbon nanotubes, tiny cylindrical structures composed of carbon atoms, boast a tensile strength 100 times greater than steel, while remaining a fraction of the weight. Similarly, graphene, a single layer of carbon atoms arranged in a two-dimensional lattice, offers extraordinary strength coupled with incredible flexibility. They are a testament to how nanotechnology might bridge aspirations between earthly capabilities and celestial applications. To visualize, imagine stacking billions of these nanotubes one atop another to form an ideally strong ribbon, a ribbon resilient enough to tether to a point in a geostationary orbit. This concept harkens to the ancient myth of the Tower of Babel, but with modern innovations fueling our ascent to the sky. The practicality of such a space elevator, however, rests not solely on technological feasibility, but also on cost considerations. Rockets, formidable and proven, consume vast resources with each launch, not to mention their environmental impact. In theory, once constructed, a space elevator could provide a more cost-effective and sustainable method, operating much like a freight train delivering payloads in a continuous manner, rather than singular, expensive bursts. Japan, known for its forward-thinking and engineering feats, has already embarked on preliminary explorations of this concept. Testing of tethered cables in microgravity environments by Japanese scientists aims to bring this dream closer to reality. Their efforts underscore a growing belief that the sky is not the limit, it is merely the beginning. As we approach the conclusion of our exploration, consider the essence of human innovation, a continuous drive to expand our reach and redefine our limitations. The concept of a space elevator challenges us to rethink our approach to exploring beyond our earthly confines. It promises a world where space access is democratized, where voyages to the vast expanse of space become as viable as booking a cross-country flight. In closing, the interplay between geostationary orbits, advanced materials like carbon nanotubes, and strategic cost models illustrate the boundless potential awaiting at the intersection of science and imagination. While today, the notion of a space elevator remains a gleaming point on the horizon, the exploration of these ideas may one day herald an era where reaching for the stars is not just poetic, but plausible.